Here we go. Hello and welcome back to Calculus 3. We are going to talk about line integrals tonight. And then go for ice cream, I guess. I don't know.
Oh, yeah. That's for all you people who do that.
So, line integrals. What are we talking about? Line integrals, right? So far, the integrals were done in 2-dimension and 3-dimension. This creature, so 2-dimension, 3-dimension. The 2-dimensional integral was done over the 1-dimensional domain. So you had x to be your input, then there was some kind of function on top, right? You will pick from A to B, and you would find the area here. Now, if you are to look this integral sideways, right, you would just see like a little line, right? That would be it. Like, this is all you see when you look sideways on, right? Then you had the integral that was over a region. So your domain used to be this. Now domain is this. And you are computing a volume for some shape that exists on top of this, whatever the shape is, Well, so this would be a 2-dimensional domain, but you are computing volume, so you're talking eventually 3D. So this was 2D, and this was 3D. What you are going to do now with the line integral is the 2D integral again, but it's in 3D. Now, it's very easy to visualize what it is. Think of a curtain that is just hanging right next to the window. So, think of a curtain. And realize that this curtain is made out of, I don't know, something that you can't straighten. So you cannot measure the area of that curtain because you can't make it straight. So you look at this, right? If you have it flat like this, right? If you have it flat, this is your Calculus 1 integral for area. And this is in 2D because this is straight and then you have height. But now, this object becomes a 3D object. But it's still thin, like a Calculus 1, right? Except now it's in space, right? So you see the difference? So Calc 1, regular integral, and then Calc 3, a line integral. Fair? So this is going to be used to calculate this area here when the domain is no longer straight x-axis. It's going to be some wavy line, therefore line integral. It's the area above that line, taking that shape. The top of the curtain does not have to be straight. It could have any function on top as well. So you are going to have two things to worry about. It will be function that you are integrating, which is how top looks like, and then the bottom, which is kind of the path that is drawn on the xy domain, which vertically up extends to the function and gives you just that film. Just think of a curtain at all times that gives you the area that you are computing. So this is a 2D integral in 3D space, 3D environment. So this is your line to be parametricized. This is where the area is. And this is where the function is on top. You can also think of this as a stencil pushing into a dough again, right? So the stencil, what is the area of the stencil that you are using, right? Which can have any kind of shape on the bottom. So now, for those of you who are interested in more in depth of the derivation of this, you will talk about the parametrization in terms of the arc length, but that's highly impractical for calculations. So we are going to parametricize over our good old parameters, t from your Calc2 class, where the circle is parametricized as x equals r cosine t and y is equal to r sine t. If you have ellipses, then those r and r become a and b, different numbers, and so on. So the parametrization equation, which we want to use for ease of calculation, here we go. So integral over some line C, call it path or line, of the function f, and then ds, that's the parametrization, the arc length parametrization. This is what we are going to do. We're going to have a to b, and then our function f will be parametricized in respect to t, and we will multiply this by the derivative of, the magnitude of the vector r prime, and then dt. Now we know that this piece here is your good old magnitude, which is the x prime of t plus y prime of t. Now, does this formula make sense at all? First of all, dimensionally, is it a 2D formula? And the answer is hopefully hell yes, right? Because you have your integral, right? And you have the function here. And this is a scalar quantity, it's just a number, does not contribute dimension-wise at all. So it is a 2D, which is what we needed. That's great. And then the parametrization, this represents the length, and then this one over here represents the height. So we're good to go in terms of height times the width. in order to get the rectangle, which is the area. So dimensionally, it does make sense. And if you are interested in the details of derivation of this, you can take a look at a book or stop by my office hours. I'll go over it with you. What else is important? This t is in between a and b. That should be clear because it's a to b dt. And I don't think there is anything else. So let's take a look at few examples and see. Average temperature on a circle. So the circle is given as x squared plus y squared less equal than 1. That means the inside and the boundary of the circle. And the temperature equation xy is given as 100 x squared plus 2y squared. All right. So this is what we have for our the setup. What is this now? If you think about this, this will be your stencil that it's pushing into this dough, and the walls of that stencil would be the area. Since this is the temperature, it will be the average temperature. So I'm supposed to integrate over C, and maybe I should just say that's your C. I'm integrating the temperature. So I need this parametrization here. Yeah, I'll just write it here. So if C was x squared plus y squared less than or equal than 1, then I can parametricize this with x equals 1 times, I don't need the 1, right? So 1 cosine t, and then y equals sine t, and t goes from 0 to 2 pi to have the entire circle. I want the whole circle. Maybe I should underline that and say whole circle. So now that I have my parametrization, you probably forgot so far, because it's been, well, sometimes like 7-8 years ago, when you wrote that vector r was the parametrization vector. You remember that? So that you can get your r prime. This is chapter 12 or 11. 11. Derivative of cosine is negative sine t. Derivative of sine is cosine. And then we find the magnitude, which will just be 1 in this case, I hope. Yeah, sine squared plus cosine squared, right? And then square root of 1 is 1. So we have that. And all you need to do now is plug everything in. So what do I have? I have integral from 0 to 2 pi. Those are my a and b from parametrization. Now the function used to be 100 times x squared. So 100 times, instead of x squared, I get to write cosine squared t plus 2 sine squared t, not theta, times 1 dt. So I hope you guys see that this is your t in terms of parameter t, and this one over here is your r prime, the magnitude. So now I will kick 100 in front of the integral, 0 to 2 pi, and then the way this is done, right, is the way to integrate squares is to use the power reducing formulas. So what I'm going to do is I'm going to kick, well, let me write it first. So first one is 1 plus cosine 2t over 2 plus, and the second one, this cancels, so it's just 1 minus cosine t 2t. I'm supposed to say 2t. There we go, much better. dt, which is further equal to 100. And now 1/2, so that's going to be 3/2 plus cosine 2t minus cosine 2t. Is this good? Oh no, this is cosine over 2. Cosine 2t, there we go. dt, which is, oops, forgot the integral, or maybe it disappeared, I'm not sure. 100, and now these two combine. So I have 0 to 2 pi 3/2 minus cosine 2t over 2. And I can kick over 2 out, make that into a 50. Integral 0 to 2 pi 3 minus cosine 2t. So now what is that equal to? That's equal to 50. I have 3t minus integral of cosine is positive sine 2t over 2 computed from 0 to 2 pi. Now I hope you see that sine term will die even when you plug in 0 or 2 pi. So the only one that counts is actually 3t. So that's going to be 50 times 6 pi equals to 300 pi. And that will be the answer. Now you know that I usually don't work out problems from the textbook. This was the problem in the textbook. I did it differently. I chose a different parametrization. So I hope that you will open your textbook and compare. I will show you now, and compare what I did and what they did. And I will explain what they did so you guys can follow easier once you decide to learn this. So first of all, note that we have the same answer of 300 pi, but it's done differently. So I will never understand why, but they are choosing their parametrization to be cosine t squared and sine t squared, radius is still 1. You can choose your parametrization. You can put this t to 100, and then you take 100 root of 2 pi to have it 0 to 2 pi when you're done, right, to parametrize. Now, with that, they are getting much worse. You see that? They're getting much worse calculation here because they have product rule when they do the derivatives. And then a lot of algebra, and they get 2t. Remember that my parametrization gave me 1. Their parametrization gives you 2t. The trade-off is the second part of the problem, because, God forbid, they don't have to use power reducing formulas, right? So all of this to, you know, no, actually, no, they do. Why the hell? I don't know. Whatever. They still have to use power reducing formulas, and then, oh no, they don't, because you can go cosine squared plus sine squared is 1. Oh, and then you can just have 1.
What?
And still have sine squared.
You could just
Maybe you want to send a letter. I don't know. I mean, handwritten. You know, if you have a fountain pen, it will look even better. Yeah, I don't know why it was done that way. So you will compare what I did and what the textbook did for that example. But as I say, you have many different ways in which you can do parametrization. So for a circle of radius r, I had x equals r cosine t, y equal r sine t, where t was between 0 and 2 pi. The textbook had r cosine t squared, y r sine t squared, 0 less than t less than square root of 2 pi. So you can have any order to parametricize circle you can go x equals r cosine t to the n, y equal r sine t to the n, 0 less than t less than nth root of 2 pi. So you can make it as annoying as you want. That's the little parametrization there. So I use this one, the most basic one you can, and it works just fine.
why do you ever even bother?
I don't know, write them a letter, figure it out. It just beats me.
Figure it out.
I have other stuff to do with my time. So it's time for 3D. So scalar line integral in 3D. It's the same thing. So now you have your function, which is in terms of parametrization x, y, and z of t, times, again, r prime, and then dt. R prime is the good old square root of x prime squared plus y prime squared. Those look like 12s, but you know they're not 12s. You know it's a prime and then squared. So I want to find an example in, this is a very long lecture, so we'll definitely have a part 2 next class. So next goal for next class is to finish this lecture and then 14.3 so that on Monday we can do only one section and review. Let's see. Problem 16 looks good. It says integrate where C is the line segment from 0, 0 to 5, 5. So your job is to first figure out the parametrization. Remember, this is your floor, x and a y. And this is the line segment in question. That's your C. So now, how do we parametricize this? Well, it's a line, right? I hope you see that this is y equal x line. So it should be very easy to parametricize this if you say that x is equal to t, and then y is equal to t as well, and the t has to go from 0 to 5. So you see that they're both going to take on the values between 0 and 5. So now I have my vector r as t, comma t. Vector r prime of the derivatives is 1, comma 1, and the magnitude of that is clearly root 2. So now we plug everything into our line integral from 0 to 5. I was integrating x squared plus y squared, I think. Yes. So x squared plus y squared would be t squared plus t squared times root 2, which is and then we have dt. So t squared plus t squared is 2, so I'm going to kick 2 root 2 out as a constant. And the only thing that I'm left inside is t squared dt. That's t cubed over 3. So 2 root 2 over 3 times t cubed from 0 to 5, which is 125 times 2, 250 root 2 over 3. So I will give you one to practice. This one looks good. We all know that's a relative when I said it looks good. C is the line segment from 141 to 363. Same steps as above. Let's see what you get. Disassembling school. This is divergence, you know? Yeah, see sections in between and then divergence. Right around the corner. So parametrization for this would be our line in 3D that you learned at some point in this course. We subtract these points to find the vector, which is a 3D carrier of the slope, right, in 3D. So that vector v, if you remember, I think that's how we called it. 3 minus 1 is 2, so 2, 2, 2 is the vector, right? And then we use the point 1, 4, 1. We set up our x, y, z 1, 4, 1 plus 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 2t, 2t, 2t. So our vector r is 1 plus 2t, comma 4 plus 2t, comma 1 plus 2t. Our r prime is 2, 2, 2, and magnitude of r prime is clearly 2 root 2. No. 2 root 3. 3 root 2. No. It's a square root of 12, yes. So 2 root 3. That's what I said. So now we are going to plug everything in the integral. But hold on. What is the value of t so that we get our numbers? If you have t equals 0, it goes 1, 4, 1. And how do I get to 3, 6, 3? 0 to 1. Exactly. We need that for limits of integration. So integral 0 to 1, we have x times y divided by z, so here is x, times y divided by z, oh, don't you love this, times 2 root 3 dt. So I can kick out 2 from the parenthesis inside, times 2 is 4 root 3, integral 0 to 1 of 2 plus t dt, which is further equal to 4 root 3 times 2t plus t squared over 2 from 0 to 1. So 4 root 3, which is now 1 plus 1/2. 0 kills everything. That's 3/2. That cancels. Twelve root 3. 2 plus 1/2 is 3/2, right? When I plug in 1, it becomes 2 plus. Oh, it's 2 plus. Wait. It's 2 plus 1/2, so that's 5. Ten root 3. Are we good on 10 root 3? So these problems have a lot of stuff going on. I hope you can see that. A lot of stuff going on. The major part is parametrization. Because parametrization gives you your R, which gives you your R prime, which gives you your R magnitude of R prime, and then also gives you the limits of integration for t. Everything is in a one spot. If you can't parametricize, not gonna be good. We can probably do one more thing before we end today. Actually, no. The next one is line integrals of vector fields, and that's, yeah, so we'll pick up with the line integrals and vector fields next class. So there will be part 2 on the stream. I will see you all next week.